Implementation and tuning of BGP continues on as we move into what I would consider some of the advanced and more difficult concepts of BGP. The first is how we can advertise networks into BGP. In part one, we established the neighbor relationships, but we quickly saw no networks were being advertised. So we'll get some networks running into BGP. BGP has auto summary, which is pathetic in my opinion. You know auto summary from EIGRP and RIP and what that does? Well, it does a very similar thing to BGP. We'll look at what it is and how to turn it off. Finally, we'll look at what I would consider two tough rules: BGP synchronization and next hop processing. They're mind blowers, so let's get going. We'll go ahead and pick up with the same topology we used in the previous implementation video. We still have the BGP neighbor sessions established. We have iBGP running between router 1 and router 4 right here. We have eBGP running between router 5 and router 4. And the neighbor relationships are established. They're just not exchanging routes because there are no routes that we've advertised into BGP. So that's where I'd like to start off. There's two ways to get networks into the BGP process. The first is through the network command, which works very different than the network command of our other routing protocols. And the second is through redistribution. Now, I guess there's a third of, well, if there's a network, further on down the line that got advertised in, that'll obviously be in BGP, but it originally had to get into BGP through one of those two methods below. So what I've done is I've added some loopbacks over here on router 5. I added 6 loopbacks for 200.1.1 through 6.0, and I've got a loopback for 50.1.1.0. Now remember, anytime we're talking about BGP, we're usually talking about public network addresses, things that are available to the public on the internet, because this is the routing protocol of the internet. So I'd like to start off by talking about the network command. Let me bring TerraTerm into the picture and clear all this stuff off. I was getting some stuff ready for this. We are actually on router 5. I'll just do a show IP interface brief to show this is the router at the quote-unquote ISP over here that has the 200 address loopbacks, and it has the 50.1.1.1. Now I'm going to advertise this network into BGP using the network command. This is the way it works. I'm going to go into global config mode, go under my router BGP process, and you type in network and the network that you'd like to advertise. Now remember, this is a little review from the previous implementation video. The network command is unlike the network command of every other routing protocol. In other routing protocols, the network command tells what networks to advertise, but it also tells what interfaces to form neighbor relationships on. In BGP, we don't have that second option because neighbor relationships are always statically configured. They're not automatically formed. So the network command just does the first piece. It tells what networks to advertise in a little different way than we've seen with other protocols. I'm going to type in network followed by what network I want to advertise. In this case, I want this one, 50. I'll just put .0.0.0. That's just like RIP. We type in the classful address right there. Now, if you do that, if you type in the network statement that way and just hit the enter key right there, BGP will look for any interface that starts with 50 on its router and automatically summarize it into this advertisement. It will send the class A advertisement out just as if it was a classful address. Now, when you're talking about a class A network that's huge, you don't want to do that on the internet unless you really do own an entire class A range, which very few people do. So network 50.0.0.0 has some arguments. We can type in, and the one I'll talk about here is mask, to specify a mask. That will allow us to specify what network mask we want to apply to this update. Now, if we do use the mask advertisement, or the mask keyword, I have to match the mask exactly as it is on this interface. This isn't a way of auto-summarizing. For example, I can't type in network 50.1.0.0 with a mask of 255.255.0.0 because that's not what this interface is. This interface is a class C subnet mask that I've assigned to that. So I have to match it exactly. I have to type in 50.1.1.0 mask 255, 255, 2550 in order to advertise that. Otherwise, it just doesn't work. There's no way to summarize on anything but the classful boundary like that with BGP without using other methods. The network command can't do it for you. There's only one of two ways. You either type in the classful one and allow BGP to advertise it as if it was a class A address, or we type in the specific subnet mask that's assigned to our interface. Let's check the results. I'm going to jump back here and type in show IP BGP, which is a command I can use to view the BGP routing table. I hit enter, and you can see that it is advertising 50.0.0.0, a next hop address of all zeros, which means itself. Now, we'll see this more and more as we go through. This star over here means it's a valid route. It is a good route. This means it's the best route, and more importantly means it's installed into the routing table. That little right angle caret right there. The key is up here. Now let's hop over to router 4. It has the neighbor relationships from the previous video and see what it sees. I'll do a show IP BGP, and sure enough, it's receiving the route 50.0.0, next hop address of 10.1.45.2. That's router 5 right there. It's got the star next to it, which means it's a valid route, and it is a best route, which means I can now type in show IP route, and I should see a BGP route in my routing table. Notice it's been summarized back to the class A address because I entered it in using the network command as just 50.0.0.0. Let's go fix that. Obviously, we don't want to have that whole class A range if we only have one chunk of it as a class C subnet. I'll go under router BGP 6500 over here, hit my no on the network command, and now I'll type in network 50.1.1.0 mask 255.255.255.0. You've got to match the exact exact match on the subnet mask. I'll type in show interface loopback 0, and you can see that I configure that with a /24, which is a class C subnet mask. That's why I had to type that exactly. Do show IP BGP. And now you can see it's being advertised with the correct mask. I hop over to router 4, show IP BGP. It's got the same information, show IP route, and it's showing up with the /24. Oh, that looked dangerous. Right here, it's saying that one has been subnetted. There's my subnet, 50.1.1.0 with a /24 subnet mask. That's the way that we can use our network command to advertise those networks. The second way that we can get networks into BGP is to do redistribution. Now, you could do redistribution of one of your internal routing protocols if you wanted to, like OSPF or EIGRP. But I'd recommend against that. Usually, your internal routing protocol is carrying your private routes. If you're redistributing them into BGP, that's not good. You don't want BGP to carry private addresses out to the internet service provider. So let me show you an example of how to do redistribution, in my opinion, the right way. We've got these networks up here, 200.1.1.1 through 6.0. So this is going to be 6 different Class C ranges. I could put them in there using the network command, or I could do redistribution. Let me jump back over to, router 5. I'm going to type in a show IP interface brief just to familiarize ourselves again. There's all our 200 addresses. Now, before I do redistribution, I want to filter it down. Like, let's say I only want to advertise those 4 into BGP. I want to do redistribution, but I only want those 4 to show up. I don't want these 2 to end up getting into BGP inappropriately, because maybe those are my private Class C ranges I use for my own DMZ. I don't want the rest of the world to know about them. So what I'll do is this. I'll type in IP access list, create an access list, a standard access list. Right, when I say IP access list, unbelievable. What iOS is this? 12.0 release 21. Well, let's use just a standard access list then. Access list 50, got to get some iOS upgrades here. And I'll do a permit Well, let's see. Would it be easier to permit the lower numbered addresses, or would it be easier to deny the upper ones? Probably deny the upper because I don't want, it's less to type. I'll put deny 200.1.5.0, deny 201.6.0, and then permit any. What I'm doing here is I'm creating a foundation access list that will deny these two, hang on, let me grab my pen here, that will deny 5 and 6 and will allow the others. Now, I'm going to use that access list inside of a route map. This is going to get a little deeper in our redistribution than we may have intended. I'm going to type in route map, we'll name it filter, and I'll just use the permit 10, and I'll say match the IP address 50. Okay, so what I've got now, let me just catch you up to speed. So I've got a route map that catches the addresses in access list 50. Now access list 50 denies these two subnets and allows everything else. Now what I'll do is I'll go under router BGP 6500. I'm going to do a redistribute command, and I don't know if you know this, but redistribute can be used for other routing protocols, but it can also be used for static routes, and it can be used for connected interfaces. Now, I'm going to type in connected because I want to send all of my, oh, I didn't even think of that. The connected interfaces will also include my WAN link, which I don't want to advertise. Ah, well, we'll fix that later. For now, I'll just do redistribute connected, and I'll follow that up with the command route map, and I named it filter. What that will do is pass all of my connected interface through that route map, which will deny the two 200.1.5.0 and 200.1.6.0 and allow everything else. So let's do a show IP BGP to see what's in our BGP routing table at this point. Nothing. Nothing. Give it some time. Trust me, BGP is slow. So we'll give it a little more time to see as it's waiting to add those networks into place. Now I'm going to do a show IP route map just to make sure. Now I'm thinking show IP route. Show route map just to make sure my route map looks okay to me. I'm just saying match the IP addresses in access list 50. Verify my access list. It is denying those, permitting everything else. Let's do it again. Show IP BGP. Ah, do you see what I'm talking about? Do you see how BGP can come back to haunt you? You think something's broken. I was kind of like, yeah, it's a little slow. Let's just check some things while we're waiting. But in the back of my mind, I'm like, oh, something's wrong. Something's, it's taking too long. BGP is just a slow protocol all around. And even though I did that redistribution command, it takes time. Now you can see that I've seriously hosed up my BGP routing table. My goal was accomplished in that only 200.1.1.2, 3, 4, all of these four subnets are coming through. The 5 and 6 got filtered out just like I'd intended. However, it saw this as a connected interface as well and redistributed it. It saw the 10 network as a connected interface. Now here's one of the topics that I have on my list to talk to you about, and that is auto summarization. BGP does it with redistributed routes. By default, auto summarization is turned on any iOS. Let me jot this on the board here. Any iOS of 12.2 release 8T or earlier. At this release, well, I should say this release and beyond. Sorry, I said that wrong. This release and beyond has auto summary off by default. Earlier versions, which I am obviously running, it doesn't even support the named access list, have auto summarization turned on. And what that means is for any redistributed route, it will automatically summarize it back to the classful boundary. So what do I need to do? Well, just like I do with EIGRP, I'm going to go under router BGP 6500 and type in no auto summary. Isn't that funny? With a routing protocol as complex as BGP, they leave a command like auto summary turned on. You can see why since iOS 12.2 release 8, which was probably about 2-3 years ago, they fixed that. They were like, obviously, this is not a feature that we want. So we can go back to the BGP routing table, and now you can see that those networks have been fixed. It's saying I am just sending the class-less version of them, which is the actual subnet mask. Now, the thing that's still goofed up is I'm advertising my private WAN link into BGP. So what I'll do is I'll also go into uh, access list 50. This is a old iOS version, so I can't easily modify it. I'll say access list 50, and I'll just do it the other way. Permit 200.1.1.1. Oops, that's 0. 200.1.1.2. 200.3. 200.4. Now what that will do is permit just those connected interfaces to be redistributed and deny everything else. The implicit deny will catch that. So now I'll do a show IP BGP. You can see my 10 network has been removed. Whew! I didn't plan on getting that complex, but you can see that the network command is essential to get those networks in there. But the redistribution command can be just as equally beneficial to get a whole bunch of networks in there at once, but typically you'll want to filter it down using a route map, just like we saw in our advanced routing our advanced routing videos when we were talking about applying route maps. This is one of the ways that we can apply it to BGP. So we've talked about the network command, redistribution, auto summarization in BGP. Now let's move on to a topic of BGP synchronization. This is a weird one. So far, we've been focused in on router 4 and router 5, but there's another router in this picture that's running BGP, and that's router 1. We haven't really been verifying that the routes are being received through the iBGP relationship that's established between these two routers. So let's do that. I'm going to hop on over to router 1 and do a show IP BGP. Let's see the BGP routing table. Oh, excellent. Good. It looks like all the routes are being received. You see that they're starts, so they're valid routes. Obviously, they're working. We can even see the next hop address and the autonomous system path that it's gone through. We've seen that we'll talk more about this field in future videos, but it came from originally the autonomous system 6500, and it was an internal network over there. The question mark comes up on any route that you redistribute because it essentially says, I don't know where this came from. That's okay, but again, we'll talk about that field later. It looks like everything's hunky-dory, but what's missing? That one. You notice all of the routes in this routing table on router 5 have the caret. If we were to go to router 4, let's do that. Show IP BGP. You can see they've all got the caret too. So what's up with router 1? Why does it not have the caret? Well, first thing I've got to mention is without a caret, you're not in the routing table. Meaning if I do a show IP route, you will not see those BGP routes in the routing table at all. All I see is some internal OSPF routes that it's learned about. So it's saying that these routes are not valid. There's two reasons for that. Let's talk about the first one right now. The rule of BGP synchronization is, let me get my definition up here. Do not use or advertise a route learned via iBGP until the same route has been learned from the internal routing protocol. Now that's a weird statement, so let me explain it. This router, router 1, learned about a route or a bunch of routes from BGP through iBGP, okay? But there is a rule that says don't use those routes if you learn about them via iBGP, and definitely don't advertise them to any other neighbors that you have until you learn about that same route from the internal routing protocol, which means OSPF. So what this rule is waiting for is OSPF to come in and tell router 1 about 200.1.4, 200.1.3. And 50. All these networks need to be backed up by OSPF in order to satisfy this BGP synchronization rule. Now you might be thinking, what on earth is that rule there for? Why would we have that? I thought BGP is going to contain the whole internet routing table. We would never send that into OSPF. Well, you're exactly correct in your thoughts, or my thoughts for you. But the reason this rule is in place is to prevent exactly what's going to happen in our screen right now. Router 1 received all of those routes. So let's say it's got 200.1.1.0 as one of the routes that it's using. Now, what on earth is that? What it's waiting for is packets that are going to be destined for that network. You know, putting routes in routing tables is one thing, but actually routing traffic to it is another. So let's say that router 1 has a network right here, and there's some computer that says, hey, router 1, I want to reach 200.1.1.0. Now, if it used that route, it will say, okay, well, let's go ahead and get you there. I'll send you to router 3 because that's the path that I need to go through to get to router 4, which gets me to router 5, which gets you to the network. But as soon as that packet hits router 3, does router 3 know about that network? Well, let's check it out. Just to verify, router 3 is running only OSPF, so it will have only OSPF routes, of which 200.1.1.0 is not one. So when it reaches router 3, since router 3 is not running BGP, the packet will be dropped. Now this rule starts to make a little more sense. Don't use or advertise a route that you learned via IBGP until you learn about the same route from your internal routing protocol. So that rule is there saying router 3 has to assure you that it can reach those BGP networks before you'll use router 3 to route that traffic. Seems like a good rule, but that's one of the things that will keep routes from being used if you're using IBGP. It's one of the rules you've got to consider. Now, here's the weird thing about it. BGP synchronization is on in iOS releases before 12.2. Here's that weird iOS version again. 12.2 release 8T. And I should say less than 12.2 release 8T. It is off in iOS releases 12.2 release 8T and later. So greater than or equal to 12.2 release 8T. Okay. Now, if BGP synchronization is off, it does not look to satisfy that rule, meaning I do not need an internal routing protocol to back me up before I'll start using those routes. The reason that they turned it off in the later iOS releases is they figured, you know what? If you're running IBGP, chances are that you are going to be running it everywhere. Let me clear off the gibberish here. You will probably be running IBGP on router 3 and router 2 if you design your network correctly, meaning you would never have a network that looks like this if you were doing it properly with OSPF. You would never force BGP routers to go through OSPF only routers to reach each other because you would know that that would goof things up. So that's why they said, let's turn BGP synchronization off by default in later iOS releases. But you still need to know about it because it's on by default in the older ones. So let me show you how to turn it off. This is one of the things we need to do to fix this problem. I go to router 1, go into global configuration mode, go into router BGP 5500, and just type in no sync, or short for no synchronization. That turns off the synchronization rule, and it would be best to do it on all the routers. I'll go to router 4 and also type in no sync because any routes that router 1 advertises, like maybe router 1 is connected to some system out here, if it's advertising them to router 4, that synchronization rule is going to prevent those from being used just as well. So that's what the synchronization rule is. Now let's go back and check to see if router 1 is using those routes. We turned off synchronization, so I'll do a show IP BGP again. No. We still do not have the best route arrow next to them. So those routes will still not show up in the routing table and they're still not being used. There's another reason, in addition to synchronization, that these routes are not being used. I don't know if you noticed it, but look at that next hop address. 10.1.45.2. Now let's think about it. Who is that? Let's look back at our network diagram. 10.1.45.2, well, it's not router 3 or router 2. It's not router 4. It's router 5? What's that all about? Router 1 is saying this is the next hop address to reach those routes, but it doesn't even know how to get to that next hop address. Look at its routing table. Do you see any route to 10.1.45 in its routing table? No. So at that point, it's looking at it going, well, I don't know how to reach those next hop, or that next hop address, so this will not be a best route. We have entered a new topic. It is known as how BGP processes the next hop addresses. Here's how it works, and it's a little odd. With BGP, the next hop processing is handled like this. For eBGP peers, it should change the next hop address on any advertised routes. So let's stop right there. That means if router 1 sends some routes to router 4, it will be the next hop address, which as of right now, router 1 is using its loopback interface as its update source. So it will say the next hop address is 1.1.1.1. Now router 4 is going to advertise those routes to router 5, and it will change the next hop address from 1.1.1.1 to itself. It will become the next hop, 10.1.45.1. So when router 5 gets it, it says, okay, that makes sense. I need to go here to reach the routes that are back here, and router 4 will take care of it from there. That's very logical because that's how every other routing protocol we've seen operates. Now this is where it gets weird. IBGP peers do not change the next hop address on advertised routes. So what this means is, let me clear this off. When I have routes being advertised, and this is exactly what's happening, from router 5, it changes the next hop address to be itself, 10.1.45.2. But this is an IBGP relationship. So when router 4 sends those routes to router 1, it will not change the next hop address. It will keep the original next hop. You might be looking at that going, well, that is really odd. Why would you design a protocol that would do that? Because obviously, router 1 needs to use router 4 to reach those networks. That's one of the hops that it goes through along the way. Well, the reason why is BGP was designed for strange environments, frame relay, Ethernet, things like that. Imagine this. Imagine that you had an Ethernet segment with 3 routers connected to it, okay? This one had some networks back here. This one had some networks back here. This one had some networks over here. Now, router 1 has a neighbor relationship with router 2. Router 2 has a neighbor relationship with router 3. Now, remember, BGP does not have a requirement that everybody be neighbors. Neighbors are statically configured. So router 1 and router 3 do not have a direct neighbor relationship. They reach each other through router 2. That's just how it's configured. And you could apply this to frame relay as well. This one advertises its, we'll say, 15 network that's sitting back here to router 2. Now that is an IBGP peer because these are all in the same autonomous system. So router 3 advertises the network to router 2. Router 2 advertises that to router 1. Since they are IBGP peers, router 2 will not change the next hop address to be itself. It will keep it the original one over here. So that way router 1 goes directly to router 3 to reach that network, and it works just great. You don't have this extra tandem hop, is what it's known as, where router 1 has to go through router 2 to reach router 3, even though they're all plugged into the same Ethernet segment. It works that same way, and this is more applicable when you get to frame relay environments that have maybe a partial mesh kind of DELCs or virtual circuits where some routers can reach each other's, others cannot, and that's where that rule comes to your advantage. But for now, it's really goofing us up because router 1 cannot reach router 5 directly. It doesn't have a path to get there because this link has not been advertised into the OSPF domain. By the way, that would be one thing we could do to solve this problem. If we advertise this into OSPF, then router 1 knows how to reach that address because it's in its internal routing table. However, you don't usually advertise external links into internal routing protocols. It's very odd to do that. So there is a BGP command that can help us fix this. I'm going to go to router 4, which, let me get our bearings, is this router right here. It's the one receiving all those routes from router 5, and the last one that actually shows them as being best routes because it knows how to reach that next hop address. And what I need to do is I need to go into the router BGP process, and I need to add another neighbor statement. You can see how these neighbor statements continue to grow and grow and grow. We end up having these gigantic neighbor statements for every single one. I'm going to type in neighbor 1.1.1.1, which is router 1. Remember, we're peering using our loopback addresses that are on each one of these routers. So I'm saying that neighbor, and here's the command. It is next hop self. One simple command changes how router 4 advertises all of its routes to router 1. Now, instead of advertising it as the next hop of this 10.1.45.2, it will advertise itself as the next hop, meaning whatever neighbor address router 4 is using. Let's go back here and do a show run real quick. Whatever neighbor address router 4 is using to communicate to router 1, which if we scroll down is, you can see update source loopback 4, so that would be 4.4.4.4. If we look at loopback 4, that's the address. It will replace all of those next hop addresses with itself. So let's verify, and this will make more sense when you see it. I'm going to jump over to router 1 and do a show IP BGP. When I do that, look at what's happened. The next hop has changed to router 4's loopback address. And look at what happened over here. All of the routes became new best routes. Those are now considered good routes. They are considered internal, and this means IBGP is how I learned about them. And if I do a show IP route, at this point, I will see all of those BGP routes added to the routing table because the criteria has been satisfied. It now knows how to reach the next hop address, and synchronization has been turned off, so I don't need OSPF to tell me about those routes too before I actually use them. So many concepts with BGP, and that's the tough part about it. With BGP, you need to know those off the top of your head. You would never be able to do a debug that says, and it says, oh, the synchronization rule is in effect. That's why these routes aren't showing up. Let me explain to you what the synchronization rule is. Those are rules that you just got to know with BGP. Same thing with the next hop self. I mean, some debugs may expose that, hey, I can't reach the next hop address and give you a clue, but without knowing the next hop processing, how BGP handles the next hop addresses, it's mind-boggling. So that's enough concepts for one video. To hit the high points, we did look at advertising networks into BGP. It's done either using the network command or redistribution. We looked at BGP auto summary, which applies directly to redistribution. If you leave it on, which is the default in the early iOS versions, then it's going to automatically summarize any networks that you redistribute back to its classful boundary, which most of the time you do not want. So you can turn that feature off just by typing in no auto. We then looked at BGP synchronization, the rule, which says do not use or advertise an internal BGP route, one you've learned via iBGP, until an internal routing protocol backs that one up. It's an attempt to try and prevent black holes in your networks. Finally, we saw how BGP handles next hop addresses. For eBGP peers, change them. For iBGP, it does not change them unless you use the next hop self command. Whew. I hope this has been informative for you, and I'd like to thank you for viewing.